basically introducing like what I've been doing like on guidance and control of the passively safe spacecraft rendezvous and proximity operations, which is paid by basically Tommaso's work. And on top of that, the basically like fundamental summary is like I have been trying to add one is like 6-DOF capability for the like RPLOT missions or like general like motion planning, and also like I have been making an effort on making things stochastic, like in a sense like basically being like resilient to like disturbances or like uncertainties. So like being motivation backgrounds, I don't think like I need to re-explain like how like diverse application like recently like RPLOT capability has, from like crewed mission to on-orbit inspection or services, debris removal, or even science missions, and so on and so on. It just keeps getting like bigger and bigger interest of like the entire space community, provided by the multi spacecraft flight systems. And as like the mission gets more and more complicated, there has been like some surge in like interest in like 6-DOF capability, which means like integrated control of like the translational motion as well as like rotational motion. Particularly like this is important for like docking, obviously for obvious reason, or even like some on-orbit inspection mission where you might want to point some target, or like you might to change like those directions, as well as, for example, there are always some constraints on like you don't want, for example, your camera or like star trackers doesn't want to like direct a certain direction like a sun, which causes some like anomaly in those like apparatus. So actually like making a plan of like such a path in 6-DOF is not really a trivial problem for like especially future more complicated distributed space systems missions. And 6-DOF control itself is like a pretty common like idea in like control community itself, but especially for like in space applications, there are a couple additional requirements. For example, it needs to be fault tolerant, which includes both passive and active safety in terms of like contingency. And another perspective is like dealing with uncertainties. Fundamentally, due to the nature of like filtering and the orbit determination, all the information contains like measurement uncertainty as well as like process noise like on the dynamics as well, which is also investigated by like a couple of past like SLAB members. And also like especially in the context of like the future space missions, autonomy is like critical like key enabling technology. So like the important factor is like we have like very limited computational resources on board. We cannot like load GPU or like really good CPU probably, and how things gonna get work done as a like entire algorithm stack is like another big challenge for space. So my problem statement has been the development of the 6-DOF spacecraft guidance and control scheme. That is one, passively safe. There is also a consideration for active safety, but especially for the last half year, I've been like focusing on passive safety in 6-DOF, and also like which has like capability to be robust to uncertainties. And third like it is tractable in onboard computational resources. So there are like many related works in like each 3 elements of like passive safety and the robustness to uncertainties and the onboard computation, especially in the context of spacecraft autonomy. So passive safety, obviously, relative orbital elements has been like giving us a great like insight on like how we can enforce like a geometrically intuitive while like sufficient condition for the safety in terms of like the translational like separation, which is evaluated by seeing the minimal distance between like our end plane and RT plane. And also like in the general control theory context, there has been a lot of like research on the what is called reachability or reachable set, which basically tells you like tells like where the agent will go, or agent will be in the safe or unsafe region after a certain period. In rotational safety, there is actually surprisingly few research on like how to be passively safe. One literature existing is a very special scenario of like single spin satellite, which spin axis is like normal to the orbital plane, which is somewhat like common like condition for like many like single agent spacecraft, while like for the RPOD missions we really will not be able to like maintain such a condition, so we need additional like development for that. And speaking of robustness on uncertainties, which is going to be a realm of like stochastic optimal control or robust optimal control. And before that, actually, one very easy way to like be robust to uncertainties or canceling disturbance is like using linear quadratic regular LQR or something like that. Also, like for the tracking, there's like development of like dual quotidian, basically applying the quotidian mechanics in the translational motion by thinking of what is called dual number, and that has been also like effort for tracking. And thinking of like the guidance perspective, there has been a lot of like effort on stochastic optimal control, and then how to make things like tractable in a sense, because it's if you think of like all this like probability distribution, things going to be fundamentally infinite dimensional. And one way is like having a chance constraint constraint on the optimal control problem to make it deterministic, or several other methods such as stochastic differential dynamic programming or covariance steering or constraint ILQG has been like developed in the last like few years. Finally, onboard computation. There are many ways to like see how to make computation tractable, like including LQR. We have like analytical solutions, so it's great. Or we also have like some closed form solutions for, especially for translational motion, so we could also leverage that. And for a more like computational optimization perspective, there has been a development of like MPC, or like especially in the nonlinear optimization context, there's a like huge deal of like how you make or how you feed a good initial guess, which is called worm studying, to nonlinear optimization, for example, like sequential convex programming. So today I'm going to talk about like four main contributions in the layer of like worm starting, of like how we get a good initial guess, and then second part is like algorithm integration, how you can like integrate like translational and rotational motion planning, and then third contribution is like how to make optimal control into stochastic form using what is called iterative covariance steering, and then finally at the optimal control formulation level, I will report some progress on how to capture the like passive safety in translational, specifically ROE space, and rotational motion from both perspectives of like integration constants and reachable set. So the general idea of like what I've been like thinking of as like this guidance scheme is like this. For example, like if you have like a specific spacecraft trying to like make a like RPod operation, and then each time step, like similar to Weiser's scheme, you will need to make a sort of like receding horizon control or MPC control. And there is like two stacks of like layers. One is basically machine learning or AI-based algorithm providing a really good initial guess, and based on that initial guess or worm-started initial guess, optimization layer will do some like nonlinear optimization, which enables us to get like a guaranteed optimality out of like like that box. So okay, let's first talk about the constraints of the passive safety. And there are like mainly two ways to define passive safety or in general safety. One way is like integration constants, or like relative, especially the good example is like relative orbital elements. Another one is like reachable sets. And the general like there's some like pros and cons in like each method. One of the big like advantage of integration constants is like there's usually like geometric constraints, geometrically intuitive constraints or closed form expressions are available, especially for the relative orbital elements. And however, like relative orbital passive safety constraints on Rn or Rt separation is usually a sufficient condition, so which doesn't necessarily capture the exact shape of the safety. So it could like leave a like some over conservative design, especially like if we want to like implement optimal control problem, like all we care is like how much we can shape off the delta V. So that might be a concern out of it. And on the contrary, reachable sets is basically considering the manifold of the dynamics, which enables us to consider basically to start from the necessary condition of the safety. So the constraints can be like exact. However, like since like it's even like very difficult to think of the shape of the manifold in like 6-dimensional space, it usually like takes us to like get some like specific knowledge, which means like things are usually unintuitive. And also like to compute the reachable set, like you usually need more computational resources. So that's going to be a huge disadvantage of it. So I would like to like compare these like constraints in the like optimal control perspective, and then like see how like each constraints like perform like or so on. So one development I've been working on is like relative orbital eminence-based passive safety as generalized as possible for like new RPOD mission. So Adam in 2018 like proposed basically like separation or safety condition on relative orbital elements for like N spacecraft in general, and then which is very like strong assumption, which is very strong condition. However, like he has like two assumptions of like energy matching, which means like delta A is like actually 0, and also like it's assuming like a circular orbit. And Tommaso like last year made another development for like energy matching condition, but for elliptic orbit. Yeah, using like Yamanaka-Ankerson's integration constants instead of like relative orbital elements based on the Cauchy-Wilshire equation. And this year, actually, there's another paper coming out from Polemy, which basically addresses the non-energy matching. So like delta A is non-zero. However, like they're still in the realm of like circular orbit. So I was basically integrating these two like papers to make non-energy matching and also like elliptic orbit passive safety. This is like pretty important for like RPOD mission usually, because like for most historical missions, like usually there is a separation in delta A, and we would like to address those issues. So the big difference of like non-energy matching and energy matching relative orbits is like since there is like a same major axis difference, it will start drifting in like a t direction. And then one way to like overcome this like drift is like to capture basically like how those like what is called instantaneous ellipses, which means like we are assuming a complete full like closed ellipse at each given point, so that like the entire trajectory is like not following that ellipse, but like it's always tangential to that ellipse. And then like by basically like having a multiple like instances of it, we can see if those like ellipses are like always like separated enough from the like the origin of like RTN frame, which is like the shape, which is the shape for spacecraft. So, and also like in like when you like look into Yamanaka-Ankerson integration constants dynamics, you see some like oscillatory like behavior in like delta A direction. So what we want to do is what you want to do is, for example, if you think of like a certain period of passive safety, let's say like t second like passive safety, it is sufficient to consider like the initial ellipse like here, and also like if you consider those like oscillatory and the diverging like behavior of like the center of the instantaneous ellipses, then it is sufficient to consider or check the passive safety of like these two ellipses at like a delta after the delta t second. And by checking these three ellipses like separated enough, you can assert this is the sufficient condition for the passive safety in both like Rn separation and RT separation. And the critical question is like now, like since the center of like ellipses like have an offset from the center of this, we really cannot use the like very clean like SGB based like EI separation formula. And one way to overcome this is basically you assume are inscribing octagon or like n-tagon out here, so that like you can only have to evaluate the like minimum distance between the center and the line, which has actually an analytical solution in 2D plane. So by checking like each separation from like this point to like each line of like this red shape, then you can like figure out by taking minimum of like these 8 edges, you can get the minimal separation of it. And this is for like one instantaneous ellipsis, and then if you apply that condition to 3 orbits, then you can get the minimal separation like for like t seconds. This is like not necessarily clean, but like the strength of like this condition is actually now like you are able to like capture like for general like probably the most general like passive safety constraints developed in our OE frame. So another way to express the passive safety in translational motion is using backward reachability. And this has been some efforts in the past years in different community. But if you think of like backward reachability, it is defined as follows. First, like if you have like a certain type of like collision, let's say, then like you have like specific region that you want to like be outside of it. For example, like a keep out zone. And if you think of like keep out zone, then there is a certain like set of like states which will go inside the keep out zone after a certain time when you propagate the natural dynamics, if that makes sense. So if you think of in the reverse way, like let's say like what is a condition of like a set of space that will get into the keep out zone after like t seconds is like basically like the idea of like backward reachable set. And since the keep out zone is usually defined as like ellipses in the RTN frame, you can actually, and using like J2 perturbed SCM or whatever linearized dynamics of ROE, you can actually have like this quadratic equation, basically having like a shape of the ellipse, like which is propagated backwards along dynamics, and then you can get constraints on the like relative orbital elements. And this is just like a set of like backward reachability at given time t, actually tj, and we basically need to get actually backward reachable 2, which basically integrates those backward reachable set throughout the like safety period, and which basically have like a union of like these sets. And furthermore, for like linear time variance systems, we would like to consider the different TF, which means that we would like to like check over like any like collision time, so that we can basically like back propagate from there, and then like we get like we want to make sure at any time like we're gonna be like passively safe. So there's like we also like have like union of like set for the TF final time, and then like that is like how we get the backward reachable 2 for like t seconds in general. And if you take a complement of that backward reachable 2, you will get basically like a passive safety constraint. So like essentially like if you're outside of that 2, you will never be like get into the keep out zone after t seconds. So those two are the translational motion, and there is also like a symmetry that should exist in rotational motion as well, which is under construction, unfortunately, for integration constants. And also like backward reachability, there is actually, for torque free motion, there exists the analytical expression of the like basically torque free motion for like basically like, so it's nonlinear state transition like mapping existing. So technically you can like just throw into that like functions of black box, and then you can also get the reachability, but like it's highly nonlinear, unlike the relative orbital elements like dynamics. So I'm still thinking of like how to evaluate this backward reachability. One way is like sampling based, which is also can be extended to the stochastic dynamics, and I'm still like it's kind of up in there. So if you have like any ideas, I would like to talk about it. So now let's go to this.
Before you continue, a quick question regarding the backward reachable set. So you define that exclusion zone in position space.
Yeah.
This is around the target space.
Yeah.
So, but in order to propagate, you need a velocity.
Yes. You can actually define. So, for example, like if you define P inverse, it's going to be a diagonal matrix because like it expresses a like a shape of ellipses, right? And then if you take like diagonal elements to like infinity for like velocity elements, you will basically get the like entire like shape of like the backward reachable set. Like having a diagonal elements infinity means basically like allows like any velocity is fine, sort of. So that's the way like you basically like develop this not only for the 3D space of like the position, but also like 6D space of like position and velocity.
And do you do that in what frame?
So this is like, so fundamentally keep out zone is defined in the RTN frame, right?
On the target.
Yes, but using the linear mapping between like RTN frame and like relative orbital elements, and then after that you can propagate on the ROE dynamics, right?
Yeah.
So basically this psi is like mapping between like integration constants or ROE to RTN frame, and like this phi is like the dynamics or state transition matrix of the relative orbital elements. So like you can only have like constraints on the relative orbital elements, but not the RTN frame. So, okay, so there comes like to the second topic. Now like this is my favorite part of the iterative covariance theory. So I would first talk about the brief motivation for why we need covariance steering. So there's, if you think of like the NPC of the spacecraft, there are like a couple ways to formulate it. And one example is like visors, which uses deterministic NPC with stochastic evaluation of the covariance, where you basically have an open loop control at each given period. And then like as you like proceed and as you get like a new estimation of like its like state, they propagate the covariance of the spacecraft for a certain period, and then like check if those can be like in the danger zone or not. And fundamentally, like if you keep using NPC, there's no way you can shrink the covariance like itself. Like that's the nature of like deterministic NPC. But if you have, for example, like a feedback controller on top of that to regulate the covariance, then like ideally, like because we have like a bigger stochastic optimal control problem, that's going to be more computational intense, but it will bring the less like triggering of the like optimization problem. So there is like a trade-off that should be like considered if you want to like keep like more frequent but computationally cheap optimization, or like you'll trigger less, and like you know like however each computation will be like larger than like the original deterministic case. So there is like a trade space actually existing in MPC. So speaking of covariance steering, the key idea is now think of like the space of like first order moment and second order moment, in a sense like you think of like state space comprised of the mean and covariance. Then you can formulate the optimal control problem like this, which basically have a objective value of like expectation. And now like the dynamics is basically linear Gaussian, but not like linear deterministic control. And then we can define the initial and the terminal condition as a normal distribution, which has like a mean and then like covariance, etc. And then all state or path constraints are going to be expressed as a chance constraints. PR indicates a probability of like these things happen. So this is the nature of like a Gaussian distribution being unbounded. So we really cannot guarantee like it will 100% satisfy the constraints. So we now have like a noise term like this, similar to like a Kalman filter. And if you introduce a state feedback controller, which has like nominal term V, this is a solution of the deterministic optimal control problem. And with a state feedback control of like xk, which is a probability distribution, subtracted by the mean, which is the again solution of the deterministic optimal control problem, then you can actually control this dynamics to a certain targeted distribution, and which is that's a really nice part of like covariance theory. And after some relaxation, I'm not going to talk about here in detail, but it's going to be turned into semi-definite programming, which is convex, so we are pretty happy. But the caveat is like there's not going to be a second order con programming, because this propagation of the covariance will yield like a linear matrix inequality, which cannot be converted into like second order constraints, unfortunately. However, there is still a convex, so we can still like push this. And also like for the nonlinear problem, this was assuming like a linearized dynamical system. But like in the very same way, convex programming can be like applied to sequential convex programming. We can also sequentially solve this problem from covariance steering to iterative covariance steering, what is called, and which is basically a development of like constraint ILQG, like linear quadratic Gaussian control.
Couple of quick questions. So you don't solve for the number of times here. So you discretize
Yes.
the horizon.
Yes.
Okay. So that's a potential drawback of the method compared with, for example, our approach based on reachable set theory, where our decision variables are also the times of the maneuvers. And so, recommendation, probably you could use MPC to cope with that problem. Second, did you try to apply this to visors?
No, actually, yeah. That's something like I really want to show, in a sense, like to compare how many NPCs can be triggered by using like a deterministic NPC and then using this. Fundamentally, like this, what this tells is like if we model like dynamics like exact, like for example, noise process or like even like innovation process, actually, we can basically, we don't have to solve things on board. Like, it's going to be fully tolerant to the uncertainty of the dynamics. But like, in fact, like, you know, like things will be like different from the like model dynamics. So like, we still probably need to trigger it. But like, there is a like potential of like reducing the NPC triggering time like much less. If that makes sense.
Well, my question was if you should try to apply to visors where we have a benchmark and see how it behaves. Yeah.
Excuse, do you have a kind of a quantification of how more is expensive to solve an SDP with respect to like an SOCP?
That's a very good question, actually. So if you think of like the state space, first of all, it's going to be like much bigger state space. For example, if you think of like 6-dot problem, then like at each time step, like there's only like 12 variables or 13 variables you need to solve for a deterministic optimal control problem. But if you think of like the covariance like as a state variable, then it's going to be 13 plus 13 squared, which is going to be like 182 or something.
This is a big.
So this is going to be a much bigger problem. So that was the reason like I'm trying to like. So unfortunately, I don't have like a quantitative like results on like how big it's going to be, but like it's essentially going to be like exponentially larger, which actually motivated me to like provide an architecture to decouple like the 6-dot problem into 3-dot.
Yeah, but before getting there are many other ways you can do to reduce the computational effort. So reduce the control horizon, adding it to go cost, for example.
Oh yeah, this is just a general optimal control, so like it could be definitely be into NPC as well.
But also the covariance, I mean, is symmetric. You can also decide to control only part of the covariance, like the diagonal terms.
Right.
So there are ways, I think, that you can play around to make it more efficient.
Yeah. Okay. So, it's a bit longer actually. Okay, so the third contribution is algorithm integration. So there is like I'm intending this to be like fully decoupled in like orbit and then like attitude, so like you don't have to trigger 6-dot like motion planning all the time. And also like for the like SCP or for the attitude control, since quotidian like covariance is usually very difficult to attain, and succeeding like Jeff's research on like process noise and error MRP, I'm thinking of like using iterative covariance steering in error MRP space, which will make us like to invent additional like SCP or motion planning scheme, which we call like multiplicative motion planning. So I would like to talk about that.
We have never heard about.
Yeah.
For SCP.
So the general idea again is like basically like having an interaction of like fully decoupled translational and then rotational motion planning given the initial guess. And so that's the reason like why if you see the state feedback control, these like block diagonal elements, off diagonal elements are 0. And the general idea is like translation for when solving translational motion planning, we basically treat like the control profile of the rotational space as a basically parameter, and then like enforce translational planner to satisfy the attitude constraints given the like control history of the rotational motion. And also like kind of vice versa for rotational like motion planning, you basically like feed the translational information to the rotational motion planning so that like translational or rotated translational constraints are still satisfied. And here the main question is like if we integrate or if we expand this to stochastic space, we need to throw like a Gaussian distribution each other and force them to like basically satisfy the chance constraint. And this is not a really trivial problem because like we are now throwing Gaussian distribution, still asking to satisfy the constraints statistically. So that's something like I need to do math a little bit more, but hopefully it's coming soon. And speaking of like the rotational side of like ICS, so again, like expressing the covariance in quaternion space is very difficult, but usually like it's much easier in error MRP space. And also like SCP has a nature of like having a reference, and then we basically like linearize that dynamics, and then we see like like how we can perturb that from there. So the idea is like why don't we just like give a reference quaternion and then solve the optimal control problem in MRP space, and then after we solve the MRP space, then bring it back to like a quaternion, so that we can like in the algorithm implementation we can still keep the quaternion, and then like hold the like error rotation error as like error MRP covariance basically. So that will like make a multiplicative OCP. This is just like for convenience, I'm just showing the deterministic formulation. Could be stochastic as well. But like you see like this error MRP affecting the control, affecting on top of the reference quaternion, which solves the entire optimal control problem as a variable of like error MRP. And one big issue is like like okay, how we solve the problem, because like this is not really linear or anything. So the idea is basically if you make a first order Taylor expansion on this expression, you basically have like a first order sensitivity, which is like affine or linear in like delta MRP. So now we can bring this into a quadratically constrained quadratic programming, which is basically a subset of like convex programming. So which should be able to solve it. I didn't have time to like bring math a little bit more, but I'm expecting this to be basically solved as a convex programming as well. So like which is nice. So finally, there's like one starting part. I don't have like much like research level update like on top of like Tomaso's art paper. So I'm gonna briefly explain this and then like skip to the results. But for example, like what we want to get is like essentially initial guess, good initial guess, and then how we infer that initial guess given the, for example, initial condition and then terminal condition is like the big problem. So we leverage the transformer architecture to basically like make transformer spit out the optimal control and the optimal state, like as we feed the optimal objective and then optimal constraint satisfaction information, as well as the, for example, initial condition. And in a very by recursively like feeding those information, like we expect transformer can basically autoregressively like infer the trajectory along the way. So that's going to be a good initial guess for the SCP or whatever nonlinear optimization afterwards. And there's recently additional paper on the MPC application as well using this. So this transformer architecture is not really just about like making the guidance for one trajectory, but it can be integrated into MPC as well. So there are some few preliminary results from both optimization side and art. Art is something I'm hoping I can put in the Caesar poster. But currently, like what I have is a sequential iterative covariance steering for rotational translational motion and deterministic SCP in a rotational space. I couldn't like expand this to ICS because originally I had an implementation all in quaternion space and then figured out, oh, I cannot express covariance in quaternion, so this is the result of it. So these blue ones are the initial guess provided by blue, originally deterministically, and then I resolved this as a like covariance steering problem, giving like adequate like terminal distribution and covariance here. And basically the idea is like you have like p-values on here, and then you want to start from here. This is the RT plane, and then you want to go like all the way up to like final approach. And once you like optimize the covariance steering, then like you see like all those like blue 3 sigma ellipses, which basically fluctuates along the trajectory. But like by applying the state feedback control, you basically like converge into like a very small covariance, like around like the like around the terminal state. And then like by using this as an initial guess, in the very same way we can feed the initial guess.
Do you meet your target? So in terms of the covariance?
Yes, because that is
Is it shown there?
like here.
On the plot?
Yeah, like this is like basically like converging it as like sort of line, but like it has like a like ellipse like plotted around here basically.
Yeah, because in your optimization problem you have a target state that is specified as a distribution with a mean and a covariance.
Yes.
And so you want to visualize that and see that you actually match that covariance.
Yeah, actually like this is just way too small. Yeah, but yeah.
You should focus on the target.
That's true. And in a very similar manner, we then like throw that into translational iterative covariance theory. Now yields like a green one, and which is actually passively safe. If you see these green trajectories, those are what is called ghost trajectories. Basically, at each point, you're releasing the spacecraft along natural dynamics, basically. So it's basically going to be uncontrolled trajectory. But all these, gray bunch of lines are avoiding like this keep out zone, which basically showing like as long as you are on this trajectory, and then suddenly if the control fails, you're still like safe for a certain period. And also like the red cone here shows like the field of view in rotational space, where like the current easiest constraint I'm having is I can just keep the the original like the origin of like the this coordinate frame inside the field of view of like this like kind of camera sort of angle, and then like you can see like all the way like those like cones or the keep out zone is always like inside this field of view throughout like the trajectory. It's basically flipping, like having a flipping maneuver here. So regarding the results of arts,
It's art.
yeah. Art is great, yeah. So that's like the part one of the result, and then part two is kind of completely different like setup, very similar trajectories as well. So to start with art, you start these basically it's machine learning, so you need a database generation. And in order to do database generation with passive safety constraints, we basically have three trajectories for each specific boundary conditions. One is convex solution without no safety constraints, so like asking just get there ultimately, which should provide a lower bound of the optimal control problem, by the way. And another one is like collision avoidance solution, which basically like asks you like we don't care about the passive safety, but do not collide to the like whatever keep out zone we define. The final one is like the SCP's passive safety solution, basically asking like, okay, be passively safe.
It's a lower bound only if you have discretized properly.
Yes. And passively safe solution exists here. And also like having two groups of initial conditions, as you can see, like one is like from here and one is from here. It's basically like if you have a higher centimeter axis, then you're gonna go back in a relative frame, and if you're lower, then you're gonna go straight. So like it doesn't make sense to try resist that dynamics on like this side basically. And here you have like a 4 terminal ports, plus minus B bar and R bar is like set, and then many trajectories are generated like this. You see like this is convex first trajectory, second trajectory, third trajectory batches, which is totally like 150K trajectories, which is now fed into art. And some like so the idea of like art, and then like this is some example like cherry-picked solutions, but what we expect, for example, is like the black one is a convex solution, and then like what we want at the end of the day is like the green solution, which is like a result of the sequential convex programming, which is passively safe. But this, you can see like the black trajectory and then like the green trajectory is pretty far, and then like you can kind of see like it takes some iteration to like get there, right? And the red one is actually the inference by art decision transformer, which you see is much closer to the like green one, which qualitatively you can see like it will probably require less iteration to like reach the passive safe trajectory of the green one or the purple one. So that's the general idea of like what we want to see. So after like getting training, we basically feed them into the test data, which was like 15K out of like 6,000 was like returned as like feasible and also like worth comparing. Worth comparing specifically means, for example, if your convex solution happen to be passively safe, then there's no point of like comparing it. So like we're choosing like a test case to be like fair comparison. If you see the iterations, like in this region, if you see like about like 2 iterations reduction compared to like convex optimization when starting the solution. So there are some effects out there. And if you see the computational time, runtime, because ours needs to infer, so like basically that also takes a computation, so it takes a bit of time. But still, like overall, for the like majority of the cases, it has an advantage in the computational time. And there are some flipping cases here, but actually these like dotted line indicates the number of samples we're training accumulatively. But like you see, like there are almost like no data available here, so it kind of makes sense. If we don't feel like training enough number of training data that satisfies the high constraint cases, then like we cannot train like neural network by definition. So that's sort of expected. But like for the like range we have enough training data, like art like shows like it basically accelerates the convergence of the SCP, which is good. And the second question we want to ask is, will art help like the SCP to provide a further, more optimal solution, or lower objective basically? And currently the answer is no. As you can see, the total objective is almost identical. And I'm wondering if you can push further by, getting more training data, or if this line is actually sort of like optimal, like lower bound, like that we reached. How fast you can get to the global optima and then how far you can go is like a bit of a different question. So we need to investigate a little bit more. But at least like it's getting like almost compatible result with like a convex SCP solution. And one concern we currently have in the test data is like there's some high infeasibility. So what it tells is like if it works, it reduces like computational time fairly well. But like also there are some like quite a few cases which is infeasible. So I'm still looking into the problem of this, and hopefully like we can reduce the infeasibility rate this a little bit more. So sorry, it was a long presentation, but conclusion is like I've been working on robust, possibly safe, and the 6-off guidance and control algorithm recently, and which comprises of like development of constraints and also like the introduction of iterative covariance steering, as well as like the decoupling of the 6-off algorithm into 2-3-off with some interaction. And especially for rotational motion, I would like to add some multiplicative motion planning algorithm. And on top of that, like bringing back to the first slide I showed, there's like a huge part that can be accelerated by art and also art and PC as well. So future work has like some these works related to this, and that's pretty much it. Thank you.